Good evening, everyone. How is everyone doing? I'm also well, thank you. So, what I will do is, I see here for Plagiarism Checker, I will add a link on ClickUp. The link will redirect you to Turnitin, and you can use it to check for plagiarism. And I'm going to create a second Turnitin link that you can use for your final submission as well. So my conference last week went really well. It was really interesting as well. So let's give another minute or two for the rest of our class friends to join us. So how did you guys find the quiz of last week? That's good to know. So compared to quiz one, quiz two marks were a lot better than quiz one. But something that surprised me is there's quite a few students that did not even attempt the quiz. So I didn't know if your timetables with tests and assignments were perhaps too packed last week and everyone was a bit too stressed. But I looked at the grade center and class list. I have 20 students that did not try the quiz. So do you guys want me to go over the memo of the quiz with you? So 80 of us know. So for the class, there is currently 156 students registered for the module. So I'm going to share my screen with you guys. Where's everyone else? That's what I'm asking as well. So in our first two lectures this semester, class participation was around about 100, between 120 and 120 in the first 2 weeks. Then it dropped down to 80. So you usually see when something is happening in a week, that is tests, assignments, then class participation drops to around about 40 people. On average, we have about between 60 and 80 people in the class. So I assume people are watching the uploaded recordings to YouTube and Google Drive. But one thing is on Google Drive, on YouTube, I can see how many views videos have. The uploaded videos to YouTube is sitting around about 6, 7 views per video. So I'm hoping everyone is watching the videos that's uploaded to Google Drive. Or to Blackboard, yes. So hopefully people are watching it. Unfortunately, it's quite in setting of online videos. It's quite difficult to keep track of who's watching the videos online. So that is what I try to do. I try to keep statistics of who is watching the videos to see if anyone is struggling. But the only thing we could see is in the mark. So you're more than welcome to use any platform to watch it. So whatever works better for you. It's a pleasure. Yeah, and it's infinite screen when you do the share screen. So it's just the one I'm looking for. Can everyone see my screen? Okay, I'm quickly going to open up the quiz. So then you will be able to see the quiz. So after the submission date, so last week Friday, you should be able to get your marks and the correct answers. But let's go through this. So ultraviolet radiation from a star, then I gave you a few options. So let's go through all these options. Then see the correct answers. Okay, I will change the settings so you can see the correct answers. So ultraviolet radiation from a star will not penetrate Earth's atmosphere and reach the ground, has a wavelength that is longer than visible light emitted by a star, has a wavelength that is shorter than X-rays emitted by the star. Then the option A and B, A and C. So ultraviolet radiation, where's ultraviolet radiation on the EM spectrum? Okay, let me see if I can zoom in. This is better. Pleasure. So when we look at ultraviolet radiation, yes, it's after visible light, and so as a wavelength that is longer than visible light, no, because ultraviolet radiation has a wavelength smaller than visible light, so B is already cancelled. Then we go to C. Has a wavelength that is shorter than X-rays. No, it's not shorter than X-rays, so C is cancelled. So then automatically when B and C is cancelled, then D and E is cancelled, and the only one is A, and it is also true. Ultraviolet radiation will not penetrate Earth's atmosphere and reach the ground. That's why it is difficult to observe at ultraviolet wavelengths, and we use that's a very good question. So the UV light we detect on Earth is primarily from the sun, because the sun is a close enough source, so we have UV radiation. But when we look at a different star, then the UV light radiation, the energy of the UV light is much, much, much smaller. So when it reaches the atmosphere, our atmosphere protects us from the UV light from different stars. So the only UV light we have is from our own sun. So if you want to observe the UV light from different stars besides our own sun, we will need a orbital observatory that we have. Then question number 2. Which of the following types of electromagnetic radiation has the highest frequency? So X-rays, visible light, radio, gamma rays, infrared. So in this list, radio will have the longest wavelengths, then infrared, then visible light, then X-rays, then gamma rays. So the shorter the wavelength, the higher the frequency. So the radiation with the highest frequency will be gamma rays. Then an atom can be excited if it emits a photon, B, if it collides with another atom or electron, C, if it absorbs a photon, D, it's A and B. So we learned an atom can be excited if it emits a photon and if it absorbs a photon. So if you watch the movie Zoom, they play around with ideas of gamma rays, and it's quite funny. Yes, I've watched the movie Zoom. I think it's with Tim Allen. There's actually quite a few movies that plays around with gamma rays. So the Hulk is gamma rays. Another one is the Fantastic Four. Then question number 4. The table below lists the spectral types of 5 stars. Which one has the greatest surface temperature? So you remember our classification, that little rhyme I put in the slides from O be a fine girl kiss me, or O be a fine guy kiss me, meaning O is the hottest, then B, then F, then G. So the hottest here with the surface temperature will be number E, so a 07 star, 07 star. Then in the HR diagram, stars with the smallest radius are found in the what part of the diagram? So the center will be more or less our main sequence. Upper left corner will be our super white giants or super blue giants. Upper right corner will be our red giants and red supergiants. Lower left corner, that is our brown dwarfs, so yes. And then the lower right corner, that won't be lower right corner because there aren't stars that is small that emits a lot of light. So the only option is D, the lower left corner. Is everybody happy with this explanation? So in your lower right corner, so in the HR diagram, star with the smallest radius are found. So in the lower right corner, we will have some stars that is extremely small radius, but are extremely luminous as well, and there's not many of them. So we're speaking about our general classification of stars. So in general, the stars on the lower left corner will also have lower radiuses on the stars on the lower right corner. So lower left corner and lower right corner, yes, you'll have dwarf stars, but we'll also have neutron stars that we will cover in the next 2 lectures. Yes, exactly. The HR diagram is like the periodic table of astronomy. So I'm going to share my lecture slides for this evening. So will the exam have similar questions? Yes, so the exam and our semester test will have similar questions as the quiz. So I'm just going to do something else before I forget. So let me just open it up. So let me quickly just find this. I quickly want to show you guys a video before we begin. So where is that I want to show you guys? So I see a few questions. Would it also be multiple choice? Yes, your test and exam will both be multiple choice. So are there past papers that we can use to study? If you find past papers for the subject, please let me know as well. Because this is now the second year I'm teaching this module. I took over this module from a previous lecturer that retired in December 2019, and he basically left nothing, so no lecture slides, no tests, no exams. Apparently, he taught this class on Blackboard, literally Blackboard in the lecture room only. So the only thing I have is what I set up last year and this year. But before the test and exam, I will provide you with a dummy test and a dummy exam for practice. Awesome. So I'm going to show you a video before we begin tonight's lecture that will explain the previous work that we did a little bit easier, and will also open up your minds on what we're going to do next in this module.
When an 8 to 20 solar mass star ends its life, it does so with a bang, a supernova. And when it's all over, there's a couple of octillion tons of superheated plasma expanding away from the explosion site at a fraction of the speed of light, a whole mess of energy released in the form of light and neutrinos, and a bizarre little ball of quantum nastiness in the center, composed almost entirely of neutrons. The properties of this neutron star are almost as bizarre as things get in the universe. And if it all seems rather alien to you, well, that's okay. For a little while, astronomers wondered if aliens really were behind what they were seeing. No, I'm not saying aliens. When we last left the core of a high-mass star, it was in a bad way. Milliseconds ago, it was fusing silicon into iron. But now it's collapsing under its own immensely powerful gravity. The collapse takes a fraction of a second, but a lot happens in that fraction of a second. In lower mass stars, the core supports itself via electron degeneracy pressure, the result of a rule in quantum mechanics that says electrons vehemently resist being squeezed together. But even electron degeneracy fails to stop the collapse if the core has a mass more than about 1.4 times the mass of the sun. That's just too much of a load to bear, and the collapse continues. Under these huge pressures, a funny thing happens. Protons, electrons, and other subatomic particles get smashed together, and they merge to form neutrons. And this happens to almost all of them. When the core collapses down to about 20 kilometers in diameter, it's essentially a ball of neutrons with some protons and electrons here and there that survive, and a crust of normal but highly compressed matter on top. When this happens, yet another effect comes into play: neutron degeneracy. Like electrons, neutrons resist being squeezed too tightly together, but this time the strength of the pressure is far, far stronger than for electrons. If the core is less than about 2.8 times the sun's mass, the collapse runs into a wall. It stops. This generates a huge shock wave, which, along with a flood of energetic subatomic particles called neutrinos, blasts outwards, blowing up the star. What's left of the core after the metaphorical smoke clears is a neutron star, one of the most bizarre objects in the universe. Such a star would be extremely weird, or really just extreme. Its mass would be more than that of the entire sun, all packed into a sphere maybe 20 kilometers across. Now, let's just stop there for a sec and let that sink in. The sun has a mass 300,000 times the Earth. Imagine packing that all into a ball the size of a small city. Too mind-boggling? Okay, think of it this way. You are mostly empty space. Every atom in your body has a nucleus made of tightly packed neutrons and protons, and electrons whizzing around outside them. If you could magnify an atom to be 100 meters across, the nucleus would be roughly the size of a marble. Imagine all that empty space between the nucleus and the electrons. That's a normal atom. But in a neutron star, all of that space would be filled with neutrons. All of it. Every nook and cranny inside the neutron star has matter in it, all the way down to the scale of an atomic nucleus. This is what gives a neutron star its mind-crushing properties. I'm now going to barrage you with very large numbers. So take a deep breath, and you might want to sit down. Neutron stars are ridiculously dense. A single cubic centimeter of neutronium, as neutron star stuff is usually called, has a mass of about 400 million tons. Want some perspective on that number? Well, very roughly, that's the total mass of every single car and truck in the United States. Imagine a couple of 100 million vehicles crushed down until they could all fit inside this six-sided die. That's neutronium. It's so dense that, as far as it's concerned, normal matter is a slightly polluted vacuum. If you set it on the ground, it would fall right through the Earth. Now, anything that dense has a huge gravitational pull. If you were on the surface of a neutron star, well, you'd be very dead, obviously, like immediately, flattened down to a thickness of just a few atoms. And that's because a typical neutron star has a surface gravity 100 billion times stronger than Earth's. I have a mass of about 77 kilos, and here on Earth, I weigh about 170 pounds. On a neutron star, I'd weigh 17 trillion pounds. That's 23,000 times the weight of the Empire State Building. But wait, there's more. In our introduction to the solar system, I mentioned that when you take a spinning object and shrink it, the spin will increase. The usual example is an ice skater drawing in his arms, increasing his rotation until he's a blur. The same is true for the star's core when it collapses into a neutron star. It may have had a very slow spin before the supernova, maybe even taking weeks to spin once. But when it shrinks down to just 20 kilometers across and becomes a neutron star, that rotation will increase by a huge factor. A freshly minted neutron star might spin several times per second. The magnetic field increases as well. A star like the sun has an overall magnetic strength not too different from the Earth's, but when that core collapses, the strength of the field skyrockets, and a neutron star can easily have a magnetic field several trillion times stronger than the sun's. That's strong enough to erase your credit card from 100,000 kilometers away. See? Ridiculous. All of these properties are brain-melting. But are they real? Could an object like this really exist? Oh my, yes. The first neutron star was detected in 1965, though not recognized for what it was at the time. A couple of years later, another one was found, and this time was correctly identified as a neutron star. But then things got weird. In 1967, Jocelyn Bell was a graduate student helping build a radio telescope. There was a persistent noise in their data they couldn't seem to fix. Bell studied it night after night, finally figuring out that the pattern wasn't a problem with their data. It was from an actual astronomical object. She had discovered the first known pulsar. What's a pulsar, you ask? Pulsars are neutron stars. In a nutshell, their rapid rotation, coupled with their incredibly strong magnetic fields, launch twin beams of energy away from the star, like the beams from a lighthouse. The beams sweep around as the star rotates, and from Earth, we see this as a pulse, a blip of increased brightness. This pulse can be detected in visible light, radio waves, and even X-rays. The spin of a neutron star is amazingly stable, making these pulses act like a very accurately timed cosmic clock. In 1967, no one could believe a natural object could do this, and this object was half-jokingly given the name LGM-1, Little Green Men 1. Now we know of over 1,000 pulsars in just our galaxy alone. And we know they're the leftover cores of massive stars that exploded. Some spin with periods many seconds or even minutes long. Some are in binary systems. Another normal star orbits them. If they're close enough together, the neutron star can whip material off the other star and feed on it. This increases the pulsar's spin. And we know of a few that have incredibly rapid rotation rates. Some spin hundreds of times per second. These are called millisecond pulsars. And if they spun much faster, the centrifugal force would rip them apart despite their tremendous gravity. Even after 1,000 years, a pulsar can still be a force to reckon with. There's a pulsar in the center of the Crab Nebula, the remains of a star that exploded to create that supernova remnant. A substantial fraction of the light emitted from the nebula is powered by the pulsar itself. Its fierce output energizes the nebula, causing it to glow brightly, even after a millennium. I'm telling you, thinking about neutron stars makes the hair on the back of my neck stand up, and I haven't even mentioned magnetars yet. Neutron stars are more than just weird little balls of neutrons. They have a crust, probably a few centimeters thick, made of highly compressed but more or less normal matter, squeezed into a kind of highly stiffened crystal state. The magnetic field of the star penetrates this crystalline crust and stretches out for quite a distance. In some neutron stars, the magnetic field is even stronger than usual and can be, get this, a quadrillion times stronger than the sun's. These uber-powerful neutron stars are given the name magnetars. They're relatively rare. Maybe 10% of all neutron stars are born as magnetars, and they have short lifetimes. The magnetic field is so strong, it acts like the brakes on a car, slowing the neutron star's spin. That spin helps power the magnetic field, so the field weakens as the star slows. But while they're around, magnetars are the most magnetic objects in the universe. And with great power comes great responsibility. If your responsibility is to be one of the scariest objects in the universe. Why? In a neutron star, the crust and magnetic field are locked together, so a change in one affects the other. The crust of the star is under incredible strain due to the intense gravity and rapid rotation. If the structure slips, it can snap, creating a starquake, like an earthquake, but just a wee bit stronger. In an earthquake, huge amounts of energy are released when the Earth's crust shifts and snaps, enough to destroy buildings and quite literally move mountains. But in a neutron star, this effect is multiplied hugely. Remember, the crust is phenomenally dense and the gravity is enormous. If the crust strains and snaps, dropping just a single centimeter, the resulting release of energy is vast beyond imagining. This energy is released as a tremendous explosion in the crust, shaking it. This also shakes the magnetic field, which reacts poorly when the sun's magnetic field throws a tantrum. We get a solar flare, which can be as powerful as billions of nuclear bombs. A magnetar flare dwarfs that into insignificance. It can be trillions of times stronger than a solar flare. In a fraction of a second, a magnetar can release as much energy as the sun gives off in 250,000 years. In 2004, astronomers were stunned when a huge blast of X-rays slammed into orbiting satellites. One of these satellites, named Swift, actually had its detectors saturated with X-rays, even though it wasn't even pointing at the source at the time. The X-rays literally came right through the side of the satellite with such intensity that Swift, which was designed to detect powerful X-ray sources, was momentarily blinded by them. The source of this X-ray burst was quickly determined to be a magnetar called SGR 1806-20, and the effects were incredible. It actually compressed the Earth's magnetic field and partially ionized the Earth's upper atmosphere. Oh, did I mention that this magnetar is 50,000 light years away? That's halfway across the galaxy. That's incredible. At a distance of 500 quadrillion kilometers, its effects were felt more strongly than a powerful flare from the sun. The good news is that there are very few magnetars like this in the galaxy, probably fewer than a dozen. Also, catastrophic explosions like the one in 2004 are rare. If one had happened any other time in the past 40 years or so, we would have detected it. And frankly, It's really cool that we had astronomical satellites orbiting the Earth which could study it. We've come a long way in understanding neutron stars since they were first discovered. But there's much about them we don't understand. Every time we find out more, we find out they're even weirder than we first thought. And yet, for all that, they're not the weirdest things in the sky. Not by a long shot. That place is held pretty securely by the other type of object created in a supernova, a black hole. Stay tuned. Today you learned that when a star between 8 and 20 times the sun's mass explodes, the core collapses to form a neutron star. Neutron stars are incredible.
So in tonight's lecture, we are looking at what happens when a star reaches the end of its life cycle. So the first couple of slides I'm going to do in Keynote because of a few animations in here. So we are going to look at what happens with giant stars, lower main sequence stars, the evolution of binary systems, and then the death of massive stars. So in this lecture, we are going to describe how stars are born and how they resist their own gravity by fusing nuclear fields in the centers to keep their internal pressure high, but they can last long but they can't last long if the fuel runs out. So there are 5 important questions we must answer in this lecture. So what happens to a star when it uses up the last of this hydrogen in its core? Secondly, what evidence shows that stars really evolve? 3, how will the sun die? 4, what happens if an evolving star is in a binary system? Then lastly, how do massive stars die? So when we think about the death of stars, it's not the Death Star, but death of stars. So it will actually be something more like this. The death of stars are important because life on Earth depends on the sun, but also because the deaths of massive stars create the atomic elements of which you are made. If stars didn't die, you wouldn't exist. So I've said numerous times in this course already that elements such as gold, silver, copper, iron, is not naturally occurring on Earth. They are formed in supergiants that went supernova, and those elements they created were scattered throughout the universe, got caught up in nebula, and were part of the forming process of planets. So here we can see the elements, how certain elements were created in the universe. So here we can see helium, hydrogen and helium is created by the Big Bang. So those are also the 2 most abundant elements in the universe. The purple ones is cosmic ray fusion. Dark blue, the exploding of massive stars. The light blue, exploding of white dwarfs. The yellow merging of neutron stars, and then the orange one, the dying of low mass stars. So you can see all the elements around us is made in the cosmos. So the white dwarfs usually just die out, and whatever remains is a floating piece of rock in space that doesn't emit any energy anymore. So with the death of stars, so let me go back. Silver ones, yes, the silver ones in this list are artificial elements that was created on Earth by making use of chemical processes in a lab. So when we speak about death of stars, there's one of two things that can happen. So the star is born in a stellar nebula. Another word I like to describe them is a stellar nursery. You can either form an average star that becomes a red giant that collapses on itself and forms a planetary nebula, and then what remains is a white dwarf. On the other hand, from our stellar nursery, we can get a massive star that evolves into a super red giant. That super red giant goes supernova. And all depending on the size of the super red giant, it can either become a neutron star or a black hole. So in this lecture, we are going to discuss this evolution process of how a star, we discussed in a previous lecture how stars are formed in matter of protostars, then how it will continue to become a white dwarf, neutron star, or black hole. Yes, Mr. Levuyo.
So can you please remind us why elements like for example why heavy elements can't necessarily undergo nuclear fusion? So can you hear me?
Sorry guys, I'm still here. I clicked a button and now all my windows has minimized all of a sudden. So I'm quickly just going to solve this problem. Not Apple problems. Apple is the best. Okay, so everything is back. Okay, so Mr. Levuyo, so what you said with okay, I see that this is, yes, I am pro Linux and I am pro Apple. So all of my servers is running on Linux. I have a few Linux virtual machines that I also use. And then my primary daily driver for a laptop is a MacBook. But when I do experiments and whatever else I need, I use Linux. So for all my experiments, I use Linux desktops. And I have a Windows virtual machine that I fire up every once in a while if I want to play a bit of games. So the last time I had a Windows machine as my daily driver was back in 2014. Speaking of which, I know this is a bit off topic. I hate Windows. I don't know if you guys, but in my family, by default, I am the IT guy. So whenever a family member has problems with their computer or whatever device, I'm the one that always needs to fix it. And last week I had a problem with a family member's Windows machine. For some reason, it became completely slow, and for some reason, the Wi-Fi doesn't want to activate on it. So in Linux or in Mac, that's an easy way to fix. You open up your terminal, you type in a few commands, and everything is sorted. But in Windows, no, you don't have such functionality, so screw Windows. So I don't like Windows, but it all depends on what you're going to do. So if you're in the scientific, so the reason I'm not using Windows is for the work I'm doing. Windows is too unstable. So when I run simulations, sometimes it takes a couple of hours to run a simulation. And when you get about 90% mark, Windows will tell you an unexpected error has occurred. So the only two platforms that are stable enough is Windows, is Linux and Apple. So for my big machines, I have a few nice servers. That is a few Xeon cores. My biggest server has 64 cores. I'm running Ubuntu 20.04 LTS server on it. And I love Linux. I love Mac OS. Which Linux though? So depending on, so the majority of the scientific community makes use of Ubuntu. So the machine I do my research on, so I have 3 servers and a virtual machine I'm running, and all of them is running Ubuntu. So continuing to Mr. Lavuyo's question, so why these elements are formed in bigger stars and outfits in the picture is when we start, for example, in a average star, such as in this diagram here, our own sun is an example of an average star as well. So it will fuse hydrogen until it gets helium. Helium will fuse to become carbon. So the easiest way to explain this is by making use of the whiteboard. So with our whiteboard, you can visualize this as different layers. So if this is the core of the star, and we have different layers around it, we analyze this layer by layer. So the inner layer, so that means the weight of the first layer must be counteracted by the fusion reaction of the core. Going to the next layer, the weight, so that means this weight is of that one as well, and at all the layers as well. So going to the next layer, meaning the weight of these layers must be counteracted and kept stable by the fusion reaction of the layer below it. So when we do hydrogen fusion, hydrogen is fused together to form helium. So that means one of these layers, this is a hydrogen core, that will fuse to become helium around it. And once the hydrogen has filled up, our helium will contract to the core and will start fusing to create carbon. So usually that process goes on, but when we reach in our own sun the carbon process, then it's not a stable process anymore, meaning the There's not enough energy to fuse carbon to create the next energy, and the outer layers becomes too heavy, and then the star dies down as a white dwarf. In a heavier sun, a super red giant, when usually they can uphold this process until you start fusing heavy elements such as iron. So when you starts fusing iron and you have an iron layer, then the core cannot produce enough energy to maintain the iron's weight, so the entire system collapses on itself, and that forms a supernova explosion. And depending on the size of the star, it can become a neutron star or it can become a black hole. And that is what we're going to discuss more deeply in this lecture.
And so when these stars go supernova, so is it sort of like like a nuclear bomb going off, like where you have the nucleus of other atoms crashing into other nucleus of other atoms, and then those atoms that are colliding with one another are splitting?
Yes, that happens. So inside a supernova, there's two reactions that follow. So the one atom is hitting another atom that can split, and that releases more energy. But what can happen as well in a supernova, while the supernova explosion cloud is expanding, it still has enough energy from the core that some elements and in the cloud can fuse to create other elements as well. And there you'll find some weird elements being formed. For example, then you don't have, for example, hydrogen fusion, but then you can get hydrogen carbon fusion or helium carbon fusion to create other elements as well.
And then, so if this goes on, so like for example, so if those atoms collide with one another, so do they? So are you saying they fuse, or do they break up and make simpler atoms?
Both happen.
Both.
Both.
So is it possible that a supernova can, like, if enough nuclear fission happens, so is it possible that um, from those simpler elements, so that like a nebula can form again, and then like you can have stars recreating themselves?
Yes, that's exactly what's happening. So when a star goes supernova, it creates the outer layers that's blown into space creates a nebula. And that nebula then restarts star formation.
But then I'm assuming enough of enough of the nuclear fission does not happen. So over time, the simpler atoms sort of um, become less, and you don't necessarily have enough of those simpler atoms to create another
Yes,
star.
and that happens over billions and billions of years.
Okay, thank you, sir.
It's a pleasure. So let me share the slides again. So can everyone see the slides? Okay, so when does cobalt form in a depth of star towards the end? So that is something we're going to discuss in this lecture as well. So when we look at this figure, we can see here what's happening. So gravity is persistent. Stars generate tremendous energy resisting their own gravity. But no star has infinite supply of fuel for this nuclear reaction. So when the fuel runs out, the star dies. So here we have the energy going out, and gravity pushing back in. So this equilibrium can be maintained as long as the star has enough fuel. Occasionally, astronomers see a formerly faint star suddenly appear much brighter in the sky, then fade away after a few weeks or months. You will learn that is what seemingly a new star in the sky is either a nova, an eruption on the surface of the stellar remnant, or a supernova, the violent explosion death of an aging massive star. A few nova, plural novae, are discovered each year. Supernovae are also so rare that only one or two occur each century in our entire galaxy. But astronomers surveying thousands of galaxies can see many supernovae flare per year. The mass of a star is critical in determining its fate. Massive stars can die in violent supernova explosions, but lower mass stars die quite quiet deaths. To follow the evolution of stars to their graves, you can start by following the life story of a sun-like medium mass star as it becomes a giant star. After that, you will learn how the stars of different masses end their lives. And on this note, you guys have probably heard during last year that the super red giant Betelgeuse has all of a sudden flared up. So that's something interesting. So last year, around about April, Betelgeuse, that is part of the Orion constellation, it all of a sudden became much brighter than it usually is, and that is usually a telltale or sign that the star is about to go supernova. So then we were interested to say, okay, now perhaps Betelgeuse is going to become or go supernova, but then it became a little bit fainter again and destabilized again. So we're not exactly sure what happened with Betelgeuse, but all evidence currently shows that it might go supernova. Massive red supergiant star V838 flared up in 2002. The expanding shell of light from the flare illuminated surrounding gas and dust that was probably ejected from the star in earlier outbursts. Bright spikes are produced by diffraction in telescopes. Planetary nebula IC1295 consists of shells of gas expelled by an aging red giant star. The star's remnant can be seen in the center of the nebula, contracting to become a white dwarf. Intense UV radiation from a central star is making the nebula glow. The prominent green color is emissions from ionized oxygen. Plan a near-infrared image of galaxy M82 and supernova 2018J observed from the Stratospheric Observatory by Infrared Astronomy. So Sophia, we've discussed Sophia in a previous lecture. The other two labeled objects are foreground stars in our own galaxy. So here are the two foreground stars. A main sequence star generates its energy by nuclear fusion reactions that combine hydrogen to make helium. The period during which the star fuses hydrogen lasts a long time, and the star remains on the main sequence for 90% of its total existence as an energy-generating star. When the hydrogen is exhausted, however, the star begins to evolve rapidly. So it now expands into a giant. So the nuclear reactions in the main sequence star core fuses hydrogen to produce helium. Because main sequence stellar cores are cooler than 100 million Kelvin, The helium can't overcome the Coulomb barrier to fuse in nuclear reactions, so it accumulates at a star center like ashes in a fireplace. Initially, this helium ash has little effect on the star, but as hydrogen is exhausted and the stellar core becomes almost pure helium, the star loses the ability to generate the nuclear energy that opposes gravity. As soon as the energy generation starts to die down, gravity begins making the core contract. So remember, in last week's slide, we discussed contraction, we discussed temperature and pressure, and now everything is coming together. Although the core of helium ash can't generate nuclear energy, it does grow hotter as it contracts because it's converting gravitational energy into thermal energy. The rising temperature heats the unprocessed hydrogen just outside the core. Hydrogen that was never before hot enough to fuse, soon hydrogen fusion begins in a spherical layer or shell around the exhausted core of the star. Like a grass fire burning outward from an exhausted campfire, the hydrogen fusion shell creeps outward, leaving helium ash behind and increasing the mass of the helium core. The flood of energy produced by the hydrogen fusion shell pushes toward the surface, heating the outer layers of the star and forcing them to expand dramatically. So in this figure, when a star runs out of hydrogen in its center, the core contracts to a small size, becomes very hot, and begins nuclear fusion in a shell, so the blue color. The outer layers of the star expand and cool. The red giant star shown here has an average density much lower than the air at Earth's surface. Here, this sign stands for solar mass of the sun, and this sign, so R with the circle and dot, stands for the solar radius of the sun. Stars like the sun become giant stars of 10 to 100 solar radii, and the most massive stars become supergiants, some 1,000 times larger than the sun. This explains the large diameters and low densities of the giant and supergiant stars. The expansion of its envelope dramatically changes the star's location in the HR diagram. Just as contraction heats a star, expansion cools it. As the outer layers of gas expand, energy is absorbed in lifting and expanding the gas. The loss of that energy lowers the temperature of the gas. Consequently, the point that represents the star in the HR diagram moves to the right relatively quickly, so in less than 1 million years for a star of 5 solar masses. A massive star moves to the right across the top of the HR diagram and becomes a supergiant, while a medium mass star like the sun becomes a red giant. So here we can see some of our famous stars. So Rigel is one of the most brightest stars in the sky. Here we have Betelgeuse, Aldebaran, our own sun. So a 15 solar mass star will become first a blue supergiant, and then pushes right, a red supergiant. A 5 solar mass sun will be a blue giant and later a red giant. A 3 solar mass sun will be a blue giant and become a red giant, and so it becomes on. So our own sun, when it starts fusing helium, it will become a red giant. As the radius of a giant star continues to increase, its enlarging surface area makes the star more luminous, moving its point upward in a HR diagram. Famous star Aldebaran, the glowing red eye of Taurus the Bull, is such a red giant with a diameter of more than 40 times that of the sun, but much cooler surface temperature than the sun. So here we can see our expansion to giants. So here we can see Aldebaran, that's in Orion, is a red giant. Something interesting I think I've discussed this in a lecture before, but let's see who has paid attention. The star cluster Pleiades, another word for them is the Seven Sisters. It is used as a logo by a company. Do you guys know which company that is? Yes, Subaru. So you guys remember from that lecture. So when we point our telescopes to Aldebaran, this is how Aldebaran looks like. So although the hydrogen fusion shell can force the envelope of the star to expand, it can't stop the contraction of the helium core. Because the core is not hot enough to fuse helium, gravity squeezes it tighter and becomes very small. When gas is compressed to such high densities, it begins to behave in surprising ways that can affect the evolution of a star. To continue the story of stellar evolution, you need to consider the behavior of gas at extremely high densities. And we will call such matter degenerate matter. Normally, the pressure in a gas depends on its temperature. The hotter a gas is, the faster its particles moves and the more pressure it exerts. The gas inside a star is ionized. So there are two kinds of particles, atomic nuclei and free electrons. Under normal conditions, the gas in a star follows the same laws relating to pressure and temperature as gases do on Earth. But if the gas is just one of two possible directions, two electrons can occupy a single energy level only if they spin in opposite directions. That level is then completely filled, and the third electron can't enter because whichever way it spins, it will be identical to one or the other of the two electrons already in the level. A low-density gas has few electrons per cubic centimeter, so there are plenty of energy levels available if a gas becomes very dense. However, nearly all of the lower energy levels are occupied. In such a gas, a moving electron can't slow down. Slowing down would decrease its energy, and there are no open energy levels for it to drop down to. It can speed up only if it can absorb enough energy to leap to the top of the energy ladder, where there are empty energy levels. So here we can see in a low density gas, the energy levels has a lot of spaces, but in high density gas, all these spaces is filled and you need more energy to leap the electron to a higher valence orbit. When a gas is so dense that electrons are not free to change their energy, astronomers call it degenerate matter. So a tip for test and exams, definition of degenerate matter. Although it is a gas, it has two peculiar properties that can affect the star. First, the degenerate gas resists compression. To compress the gas requires pushing against the moving electrons, and changing their motion means changing their energy. That requires tremendous effort because you must boost them to the top of the energy ladder. That is why degenerate matter, though still a gas, is harder to compress than the toughest hardened steel. Second, the pressure of degenerate gas does not depend on temperature. To see why, note that the pressure depends on the speed of the electrons, which can't be changed without tremendous effort. The temperature, however, depends on the motion of the particles in a gas, both electrons and nuclei. If you add heat to the gas, most of that energy goes to speed up the motions of the nuclei, which move slowly and don't contribute much to the pressure. Only a few electrons can absorb energy, enough energy to reach the empty energy levels at the top of the energy ladder. This means that changing the temperature of the gas has almost no effect on its pressure. These two properties of degenerate matter becomes important when stars end their main sequence life. Eventually, many stars collapse into white dwarfs, and you will discover that these tiny stars are made of degenerate matter. But long before that, the cores of many giant stars become so dense that they are degenerate, a situation that can produce a cosmic bomb. So now we're going to look at helium fusion. So hydrogen fusion in main sequence stars leaves behind helium ash. Free helium nuclei can collide to make a carbon nucleus in what is called the triple alpha process. So nuclear physicists refer to helium nuclei as alpha particles. The helium ash in the core of main sequence stars is so cool to fuse because helium nuclei have positive charges twice that of hydrogen nuclei. So the helium nuclei needs to move very fast to overcome the higher Coulomb barrier. As a giant star fuses hydrogen to helium in an expanding shell, its inner core of helium contracts and grows hotter. When the temperature of the core finally reaches 100 million Kelvin, it begins to fuse helium nuclei to make carbon. How a star begins helium fusion depends on its mass. Stars more massive than about 3 solar masses contract rapidly, the helium-rich cores heat up, and helium fusion begins gradually. Less massive stars evolve more slowly, and their cores contract so much that a gas becomes degenerate. On Earth, a teaspoon of the gas would weigh as much as a large truck. In this degenerate matter, the pressure does not depend on the temperature, and that means the pressure-temperature thermostat does not regulate energy production. So you can see where this is leading up to with the pressure-temperature thermostat. When the temperature becomes hot enough, helium fusion begins to make energy and the temperature rises. But pressure does not increase because the gas is degenerate. The higher temperature increases the helium fusion even further, and the result is a runaway explosion called the helium flash, in which for a few minutes the core of the star can generate more energy per second than does an entire galaxy. Although the helium flash is sudden and powerful, it does not destroy the star. In fact, you were observing a giant star as it experienced the helium flash, you would probably see no outward evidence of the eruption. The helium core is quite small, and all of the energy of the explosion is absorbed by the distended envelope. In addition, the helium flash is a very short-lived event in the life of a star. In a matter of minutes to hours, the core of the star becomes so hot that a significant number of electrons get boosted to empty energy levels at the top of the energy ladder. That increases the pressure, ends the degenerate conditions, and the pressure-temperature thermostat brings the helium fusion under control. From that point on, the star proceeds to fuse helium steadily in its core. There are two reasons why the helium flash is important. First, it is so violent and sudden that it makes it difficult to compute models of stars and be sure how they evolve. Astronomers have to exercise ingenuity to get past the helium flash and follow the further evolution of stars. Second, the helium flash is a good illustration of how science reveals a hidden universe. Astronomers would never have known about the helium flash were it not for the theoretical calculations of stellar models. The Sun will experience a helium flash in 6 to 8 billion years from now. But stars less massive than about 0.4 solar mass never get hot enough to ignite helium. Stars more massive than 3 solar masses ignite helium before their contracting cores become degenerate. So in this figure, when a main sequence star exhausts the hydrogen in its core, it evolves rapidly to the right in the HR diagram as it expands to become a cool giant. It then follows a looping path as it fuses helium in its core and then fuses helium in a shell. So compare this figure to the one we did in the beginning of this chapter. So what happens is, here we will have our star, and then it will start fusing helium, and then we'll have its flash, and then we'll go a little bit brighter, and then the helium fusion continues. Helium fusion produces carbon, and some of the carbon nuclei absorb helium nuclei to form oxygen. A few of the oxygen nuclei can absorb helium nuclei and form neon and then magnesium. Some of these reactions releases neutrinos, which, having no charge, are more easily absorbed by nuclei to gradually build even heavier nuclei. These reactions are not important as energy producers, but they are slow cooker processes that form small traces of heavier elements right up to bismuth with atomic weight of 209, nearly 4 times heavier than iron. Many of the atoms in your body were produced this way. So here is the famous quote of astronomer Carl Sagan. We are made of star stuff. Our bodies are made of star stuff. There are pieces of star within us all. As the helium fuel is used up, the accumulation of carbon and oxygen atoms creates an inert core too cool to fuse. Once again, the core contracts and heats up, and soon a helium fusion shell ignites below the hydrogen fusion shell. Now that a star makes energy in 2 fusion shells, it quickly expands and its surface cools once again. The point that represents the HR diagram moves back to the right, completing the loop. What happens to a star after helium fusion depends on its mass. But no matter what tricks the star plays to delay its end, it can't survive long. It must eventually collapse and end its career as a star. So here we are back to this image where it completes its loop and moves back to the right again. So where do we get our evidence of stellar evolution? The easier way is to look at star clusters. So just as Sherlock Holmes studies peculiar dust on a lampshade as evidence that will solve a mystery, astronomers look at star clusters and say, a photo of a star cluster freezes a moment in the evolution of the clusters and makes the evolution of stars visible to human observers. So I'm going to open the floor to you guys and start a little bit of a discussion. Why or how can star clusters tell us about the evolution of stars? Yes, Mr. Lavuyo.
Because stars are quote unquote born in a what is it called? A stellar nursery.
Yes.
Most of those stars would be a similar age, but they also would have variations. So most star clusters, you would see that the stars are usually have similar colors. So some of them, most of them would be blue, and then other star clusters, the older ones would be much red, would be more red. And so looking at those different types of different color star clusters, you can see how stars evolve.
Ms. Lavuyo, you are spot on. So let's discuss this a little bit further. So because they formed nearly simultaneously from the same gas cloud, the stars in a cluster have about the same age and composition. So any differences you see among them are due to their differences in mass. That means that when you look at a cluster, you can see the effects of stellar evolution as the effects on otherwise similar stars of different masses. So there are 3 important aspects of star clusters. There are 2 kinds of clusters, open clusters and globular clusters. They look different, but they are similar in the way that stars evolve. Then secondly, You can estimate the age of a star cluster by observing the turn-off point in your distribution of the point that represents its stars on an HR diagram. Then finally, the shape of a star cluster's HR diagram is governed by the evolutionary paths the stars take. The HR diagram of older clusters are especially clear in outlining how stars evolve away from the main sequence to the giant region, then move left along the horizontal branch before evolving back into the giant region. By comparing clusters of different ages, you can visualize how stars evolve, almost as if you were watching a film of a star cluster evolving over billions of years. Contracting stars heat up by converting gravitational energy into thermal energy. Low-mass stars have little gravitational energy, so when they contract, they don't get very hot. This limits the fields they can ignite. In the previous chapter, you saw that protostars less massive than 0.08 solar mass can't get hot enough to ignite hydrogen. This section will concentrate on stars more massive than 0.08 solar mass, but no more than a few times the mass of the Sun. Structural differences divide the lower main sequence stars into two subgroups: very low mass red dwarfs and medium mass stars such as the Sun. The critical difference between two groups is the extent of interior convection. If the star is convective, fuel is constantly mixed and its resulting evolution is drastically altered. So red dwarfs, so that's stars between 0 and 0.08 and about 0.4 solar masses. The red dwarfs have two advantages over more massive stars. First, they have very small masses, and that means they have very little weight to support. Their pressure temperature thermostats are set low, and they consume the hydrogen fuel very slowly. The red dwarfs have a second advantage, that they are totally convective. That is, they are stirred by circulating currents of hot gas, rising from the interior of cool gas sinking inward. This means the star is mixed like a pot of soup that is constantly stirred as it cooks. Hydrogen is consumed uniformly throughout the star, which means the star is not limited to the fuel in its core. It can use all of its hydrogen, prolonging its life on the main sequence. Because a red dwarf is mixed by convection, it can't develop an inert helium core surrounded by unprocessed hydrogen. Therefore, it can never ignite the hydrogen shell and can't become a giant star. What astronomers know about stellar evolution indicates that these red dwarfs should use up nearly all of their hydrogen and live very long lives on the lower main sequence, surviving for 100 billion years or more. Of course, astronomers can't test this part of their theories because the universe is only 13.8 billion years old. So not a single red dwarf has died of old age anywhere in the universe. Every red dwarf that has ever been born is still shining today. And have you guys ever thought about that? Then with the red dwarfs, we have three different classifications. We have our L dwarfs. There are about 1,000 known. The surface temperatures is 1,500 Kelvin to 3,000 Kelvin. Then we have our T dwarfs. That is a lot cooler. There's about 500 known. Surface temperatures between 500 Kelvin and 1,500 Kelvin. And then we have white dwarfs. About 17 known. Surface temperatures 250 Kelvin to 500 Kelvin. So also black holes have long lifespans. Yes, and that is something we're going to discuss as well. Now we're going to start looking at medium mass stars, such as our own Sun. So stars like the Sun eventually become hot enough to ignite helium as they pass through their giant phase. But if they contain less than 4 solar masses, they do not get hot enough to ignite carbon, the next fuel after helium. So when they reach that impasse, they collapse and become white dwarfs. There are two keys to the evolution of these sun-like stars: the lack of complete mixing and mass loss. The interiors of medium mass stars are not completely mixed. Stars of 1.1 solar masses or less have no convection near their centers, so they are not mixed at all. So the convection occurs in close to the surface of those stars. The stars with a mass greater than 1.1 solar masses have small zones of convection at the centers, but this mixes no more than about 12% of the star's mass. Medium mass stars, whether they have convective cores or not, are not thoroughly mixed, and the helium ash accumulates in an inert helium core surrounded by unprocessed hydrogen. So here we can see a nice illustration of this. Inside the main sequence stars, the more massive the star, have small convective interiors and radiative envelopes. Stars like the Sun have radiative interiors and convective envelopes. The lowest mass stars are convective throughout. The cores of the stars where nuclear fusion occurs are small portions of the interiors. So now we're going to discuss planetary nebula. So when a medium mass star like the Sun becomes a distended giant, its atmosphere cools. As it cools, it becomes more opaque, and light has to push against it to escape. At the same time, the fusion shells become so thin they are unstable and begins to flare, which also pushes the atmosphere outward. Because of this outward pressure, an aging giant can expel its outer atmosphere in repeated surges to form one of the most intriguing objects in astronomy, a planetary nebula. So called because through a small telescope it looks like the greenish blue disk of a planet like Uranus or Neptune, so the rings around Neptune, Uranus, and Saturn. It's also examples of it. In fact, a planetary nebula has nothing to do with a planet. It is composed of ionized gases expelled by a dying star. Yes, Mr. Lavuyo.
Sir, can you please understand? Not understand. Can you please explain, like how light, like for example, so how different wavelengths of light can pass through, like certain molecules, but others cannot?
Okay, so the easiest way to describe this is, let me get the whiteboard out again. Okay, so I'm going to ask all of you guys, so let's see if we can get a nice discussion started. Have you guys ever thought of how a microwave works? So in your microwave, you will have a component called a magnetron. So the magnetron uses microwaves, so it's electromagnetic radiation where the wavelength is only a few millimeters long. And when that energy hits your food, the food particles becomes to vibrate and becomes hotter. But if you looked at your microwave, that you look through the glass door, have you guys noticed there's a small mesh grid? So what actually is happening when we have our mesh grid, so let me draw it. We have our mesh grid. So let's draw it. So we have our mesh grid. Let's see, it's not one of the best drawings, but this will work. So that means our incoming microwaves, the physical wavelengths. So usually when we speak about as wavelengths, we speak about it as traveling as a sinusoidal wave. So that means that sinusoidal wave is larger than these mesh openings. So when it's larger than these mesh openings, it cannot pass through this mesh. So let me get a different color. This mesh. But once a wavelength is smaller than these mesh openings, then it can pass through this mesh. So in your microwave, that mesh grid on the front, the microwaves being used to heat up your food, the wavelength is physically larger than the openings in that mesh. So for the wavelength, it sees this door as a solid piece of metal because it can't go through these gaps, but a smaller wavelength can pass us through. So that's how you shield yourself from microwaves in a microwave. So the same principle works with visible light. It depends on how closely compact the molecules are of these certain materials and gases. So for visible light, if the wavelength is small enough to fit through the gaps between the molecules and particles, we can see it. If the wavelength is longer, then it won't be able to pass through the gaps and we won't be able to see the light. Yes, Mr. Groenewald, so it's exactly like the low frequency arrays of the SKA. So that basically comes down to, again, antenna design, but that is how it works. So Mr. Lavuyo, does that answer your question?
Yes, sir. Sir, in a nebula, sir, is like, sir, since, like, for example, if the nebula is dense enough, does that mean that the light gets trapped inside and, like, is it like reflected inside the like within the nebula, or is it absorbed by the other molecules within the nebula?
Okay, so in nebula, we get a few nebula. So depending on what molecules there are, some of these light can be reflected in the nebula. Some of them can be completely blocked out. We cannot see it. So when we look at some nebula, we can call it a dark nebula. That's when visible light can't escape the core of the nebula, but other wavelengths can escape, such as X-rays, gamma rays, microwaves. Then we can observe the nebula at different frequencies.
Thank you, sir.
It's a pleasure. So let me get back to the slides. For those of you that's interested, it's on YouTube as well. Last Sunday night, there was an insert on Carte Blanche about the MeerKAT telescope. So here we will see a planetary nebula. So here we will see our star. It's starting to push away the outer layers of its atmosphere, and it creates this nebula that we call a planetary nebula. This is the same as planetary nebula, but only at different wavelengths. So there are 4 important points on planetary nebula. You can understand what planetary nebula are like by using simple observational principles such as Kirchhoff's laws and the Doppler effect. Have you guys done Kirchhoff's laws before? Okay, so I did not prepare a slide of Kirchhoff's laws, but I will quickly make a note. In tomorrow night's evening, would you guys like me to quickly go over Kirchhoff's laws? Okay, let me make a note of it. Okay, I made a note. So Kirchhoff is one of those physicists. He had a finger in too many pies, and you will learn a lot about his work in different modules as well. Then secondly, notice the model that astronomers have developed to explain planetary nebula. The real nebula are more complex than the simple model of a slow wind and a fast wind, but a model provides a way to organize the observed phenomena. Then thirdly, opposite directed jets, so much like the bipolar flows from protostars, produce many of the asymmetries seen in planetary nebula. Then lastly, the star itself must contract into a white dwarf. Now we're going to start discussing white dwarfs. So when you survey the stars, you discover that white dwarfs are the second most common kind of star. Only red dwarfs are more abundant. Now you can recognize the billions of white dwarfs in our galaxy as the remains of medium mass stars. The first white dwarf discovered was the famed companion to famous star Sirius. So Sirius is a double star. In that visual binary system, the bright star is Sirius A, the white dwarf is Sirius B. It is 9,000 times fainter than the famous star Sirius, but Sirius is one of the brightest stars in the night sky. The orbital motions of the stars reveal that a white dwarf contains 0.98 solar mass, and its blue-white color tells you that its surface is hot and is about at 45,000 Kelvin. Because it is both very hot and very low luminosity, it must have a small surface area. It is about the size of Earth, so dividing its mass by its volume reveals it's very dense, about 2 times 10 to the power 6 grams per cubic centimeters. On Earth, a teaspoon of Sirius B material would weigh more than 10 tons. A normal star is supported by energy flowing outward from its core, but a white dwarf can't generate energy by nuclear fusion. It has exhausted its hydrogen and helium fuels and converted them into carbon and oxygen. When a star collapses into a white dwarf, it converts gravitational energy into thermal energy. Its interior becomes very hot, but it can't get hot enough to fuse its carbon-oxygen interior. Instead, the star contracts until its core becomes degenerate. Although a tremendous amount of energy flows out of the hot interior, it is not the energy flow that supports the star. The white dwarf is supported against its own gravity by the pressure of its degenerate electrons. A white dwarf future is bleak. As it radiates energy into space, its temperature gradually falls, but it can't shrink any smaller because its degenerate electrons resist getting closer together. Degenerate matter is a very good thermal conductor, so as heat flows to the surface and escapes into space, the white dwarf gets fainter and cooler, moving downward and to the right in the HR diagram because a white dwarf contains a tremendous amount of heat. It needs billions of years to radiate that heat through its small surface area. Eventually, such objects may become cold and dark, so-called black dwarfs. Our galaxy is not old enough to contain a black dwarf. The Sun, the coolest white dwarfs in our galaxy, are about the temperature of the Sun. Perhaps the most interesting thing astronomers have learned about white dwarfs has come from mathematical models. The equations predict that if you add mass to a white dwarf, its radius will shrink because added mass will increase its gravity and squeeze it tighter. If you add enough to raise its total mass to about 1.4 solar masses, the equations predict that its radius will shrink to 0. This is called the Chandrasekhar limit of the Subrahmanyan Chandrasekhar, the astronomer who discovered it. So there's actually a movie about him that I would recommend you guys to watch. The movie's name is The Man That Could Count to Infinity. Infinity. So this definition right here is a very, very, very important definition. And I'm going to ask it in the test and exams as a hint. And before we go on, do you all grasp this definition? So, okay, let me go through it again. So just to understand the definition, we're going to discuss this in the next following slides so you understand it better. But what Jean described, the physical math of this, and if you have a white dwarf and you add mass to it, so you keep throwing more mass on it, and you increase the white dwarf's mass to 1.4 solar masses, its radius will shrink. So what it means is, because it's already compressed so much as degenerate matter, but if you add more mass, it still needs to be compressed a little bit. So what the math tells us is, if we increase a white dwarf's mass to 1.4 solar masses, its radius will shrink to 0. And do you guys know what that means? Not really boom time, but a formation of a black hole. Yes, Mr. Levuyo. And Mr. van der Berg. Ah, sorry, you're correct. It was Ramajan. Yes, sorry, I'm confused. There's a specific movie where they about Chandrasekhar as well. Yes, Mr. Levuyo.
So out of all the fundamental forces, sir, is gravity the only one that sort of can change when it comes to like its magnitude?
All the forces in the fundamental forces can change in magnitude, but I think what you are asking is the force or the magnitude scale of gravity is the one that's most noticeable and that can change very much.
But then, so we told that the force of gravity is like the weakest out of all the fundamental forces, but then yet it still can overcome the like the nuclear forces, which are sort of repelling all other molecules.
Yes. So if you think about it, if you think of the star itself, even though gravity of a star is so immense, the nuclear forces of the star is much more than the gravitational forces.
But then, so if you are adding like more molecules, shouldn't that mean that like the molecular, like the not the molecular forces, but like the nuclear forces, so that are sort of pushing everything apart? So wouldn't that sort of also be contributing to the like, for example, like not the like what's the opposite of shrinking? Expand the expansion, yes, the expansion of should that not contribute to the expansion of the star itself?
Yes, it does, until it reaches a certain point. Then gravity overcomes those forces, and then the system starts to collapse.
Okay, thank you, sir.
Pleasure. So that's why it's called a black hole. It's called a singularity. A singularity is basically a point. So when we're speaking about something that is radius equals to 0, it can still be a very, very, very small point, and that's why it's called a singularity. So here we can see how the Chandrasekhar limit is working. So the more massive a white dwarf is, the smaller its radius. So objects more massive than the Chandrasekhar limit of 1.4 solar masses can't be white dwarfs, so what the hell are they? So here we can see a nice white dwarf with its planetary nebula. This is called Thor's Helmet. And here is a visualization of millimeter radio data of a different white dwarf. I'm just going to look here. I think I may have another animation in this slide. Yes. So I'm just quickly going to stop this here. I'm going to share different slides. So stars in a binary system can evolve independently of each other if their orbits are large. In this situation, one of the stars can swell into a giant and collapse without disturbing its companion. But some binary stars orbit as close to each other as 0.1 AU. And when one of those stars begins to swell into a giant, its companion can be strongly affected. These interacting binary stars are interesting in their own way. The stars share a complicated history and can experience strange and violent phenomena as they evolved. But such systems are also important because they can help astronomers understand the ultimate fate of stars. So in the next chapters, we will see how astronomers search for black holes in interesting binary systems. Journey of a Star. Thank you, Mr. Groenewald. Let me just share the slides on Blackboard again. So does the Schwarzschild radius apply to stars? Yes, and that's something we're going to discuss in this lecture as well. So you see, all these terms you've heard before is now building up to what we are learning. So binary stars can sometimes interact by transferring mass from one star to the other by gravitational fields of two stars, combined with the rotation of the binary system to find a dumbbell-shaped volume around a pair of stars called the Roche lobes. The surface of this volume is called a Roche surface. So in this, we have our two binary stars. Here we have star, the biggest star, the smaller companion star. This will be one Roche lobe, and this will be the other Roche lobe. The size of Roche lobes depend on the masses of the stars and the distance between the stars. If the stars are far apart, the lobes are very large, and the stars can easily retain their own material. If the stars are close together, however, the lobes are small and can interfere with the evolution of the stars. Matter inside each star's Roche lobe is gravitationally bound to the star, but matter that leaves a star Roche lobe can fall onto the other star or leave the binary system completely. The Lagrange points are places in the orbital plane of a binary star system where a bit of matter can reach stability. For astronomers, the most important of these points is the inner Lagrange point where the two Roche lobes meet. So something interesting, somewhere in your second or third year, you will be doing Lagrangian mechanics. So we know in classical mechanics, we have our normal laws of motion and equations, and we can basically calculate trajectory motion and a few other things. But with classical mechanics, there becomes too many unknowns in the equations to solve. So another way you will learn to solve classical mechanics and motion will be making use of Lagrangian mechanics. And in Lagrangian mechanics, the most important things you need to know is where the system is stable. Then you can calculate everything of the system you want. So right here, we will see our inner Lagrangian point L1, another Lagrangian point, another Lagrangian point, another one over here, another one over here, and at those points, that's where the system is stable. But at our L1 point is the most important, and that is where the two Roche lobes meet. In general, there are only two ways matter can escape from a star and reach the inner Lagrange point. First, if a star has a strong stellar wind, some of the gas blowing away from it can pass through the inner Lagrange point and be captured by the other star. And secondly, if an evolving star expands so far that it fills its Roche lobe, which can occur if the stars are close together and the lobes are small, then matter can overflow through the inner Lagrange point onto the other star. Mass transfer driven by stellar wind tends to be slow, but mass can be transferred rapidly by an expanding star. So evolution with mass transfer. So mass transfer between stars can affect the evolution of stars in surprising ways. In fact, it is the solution to a problem that puzzled astronomers for many years. In some binary system, the less massive star becomes a giant, while the more massive star is still in the main sequence. If higher mass evolve faster than lower mass stars, how do lower mass stars in such binaries manage to leave the main sequence first? This is called the Agol paradox, after the binary system Agol. So here's the Agol paradox explained. The paradox can be explained by mass extraction. The 0.8 solar mass subgiant star used to be more massive of the two stars. When the Agol binary system formed, it was a 3 solar mass main sequence star with a 1.5 solar mass main sequence companion. As the 3 solar mass star evolved into a red giant, tidal forces began to deform the star. The surface got close enough to the other star, so the gravity pulled matter from it onto the other. So here we can see these started to expand and starting to pull matter onto the other star. As a result of mass exchange today, the giant lost 2.2 solar mass and shrunk into a subgiant star. The companion is now 3.7 solar mass star. So here we can see it became a solar mass star. So you're all happy with this explanation? Awesome. So I see our time is almost up, so I'm just going to finish this part of star evolution. So mass transfer explains how this could happen. Imagine a binary system that contains a 5 solar mass star and a 1 solar mass companion. The two stars formed at the same time, so the higher mass star, evolving faster, leaves the main sequence first. When it expands into a giant, however, it fills its Roche lobes and transfers matter to the lower mass companion. The higher mass star loses mass, evolves into a lower mass star, and a companion gains mass and becomes high mass star that is still on the main sequence. That is the reason why there could be a system such as Agol that contains a 5 solar mass main sequence star and a 1 solar mass giant. So here we can see what's happening. We have star A, star B, so it fills its Roche lobes and matter transfer starts to fall onto star A. Then star B loses mass and star A gains mass. Then what happens is then star A becomes a massive main sequence star with a lower mass giant companion. And then star A has now become a giant and loses mass back to the white dwarf star, remains on B. So once this Roche lobe is filled, the mass is formed back on the smaller star again. And I think, ladies and gentlemen, we're going to call this a evening. We will finish this lecture tomorrow evening. I will still remain active for a minute or two if you have any questions. Otherwise, have a great evening, and I will see you guys tomorrow evening. Yes, Mr. Lubuyo.
So with this process that's happening, the star that was first a higher mass star, does the matter that it loses, like it's no longer hydrogen, right? It's the fused, element.
Yeah. Yes, it's the fused element, yes.
But then, okay, so then when it loses its mass, does that mean that the star B also fuses the mass, the matter that it's gaining?
Yes.
So how long can this process happen for? Because it's like you subbing matter and then you still like trying to stay alive.
So this process can go on for billions of years, because now when you have a problem, so the one star has burned through all of its fission material, so then it starts to expand to the temperature thermostat controls the process. Then it gets material from the other star, and it can continuous fusion. And when the other star starts contracting and starts pushing out its outer layers, then it becomes fills up as Roche lobe, and it can steal material from the other star again. So between these two stars, there will be an ever going of borrowing and stealing and transferring of matter between one and another, and that will continue on until both stars evolve separately on the HR diagram. So usually when this happens there's a few possibilities that can happen at the end of this life cycle. So what can happen is these two stars can combine to become one giant star that will then continue on its processes, or one star can be flung out of the binary system, so that can also happen, or both stars can die off as neutron stars.
So it's not that this process happens forever, like one of those things has to happen.
Yes, one of those things has to happen. So it basically prolongs the life of both stars.
And hypothetically, if none of those situations would happen, then would would the stars sort of live longer than ordinary stars?
Yes, so both of these two stars, although they are stealing material from one another and transferring it, their lifetimes will be much longer than any other stars.
Until like for example, so you said there's an element in which it stops, like it becomes unstable. So once it reaches that that phase, then the transferring sort of becomes useless.
Yes.
Okay, thank you, sir.
Pleasure. So see here, how does an atom emit a photon? So once you have an atom and you have a electron falling from a high valence orbit to a lower valence orbit, then that releases a photon. Sir, can you share the link of the video we watched in the beginning of class? Yes, I will share that as well. So can you please repeat what a Roche lobe is? So let me go back a couple of slides. So when we look at Roche lobes, so binary stars interact with one another. So the gravitational fields of two stars combined with the rotation of the binary system define a dumbbell-shaped volume around a pair of stars. So this star that have a region around it that has gravitational pull on it. And this star around here will have gravitational pull and also magnetic pull. And these two areas form this dumbbell-shaped object, and that is called the Roche lobes. Then another question, off topic. First other question, can a system eventually become a black hole? Yes, that can become one of the outcomes of such a system. Then off-topic question, if energy cannot be created or destroyed, how is it possible that the universe will die? But then that means you must also ask how the universe came to existence too, if we follow this analogy. Yes. So when we follow this analogy, all the energy we have and know was released in the explosion of the Big Bang. But once the universe dies out, that energy needs to be converted into a different form, and currently we don't know what that will be yet. So, ladies and gentlemen, I'm going to stop the recording.